Good afternoon. Welcome back to the third lecture in the Concepts of Programming Languages course. The third lecture will also tackle a concept in the logic programming paradigm. The concept that we will be tackling this time is structures. The question is, how could we define structures in Prolog? And we will try always actually to compare it with structures and in general data structures in Java. Once we want to implement a data structure in Java, most probably what we have to do is we have actually to go and define a class, define the instance variables in the class as well as the constructor, and then once we want to use a structure, we create an instance of the class itself. In Prolog, the whole thing actually will be dealt in a totally different way. Now, let me go back actually to the programs that we introduced the last two sessions. Let me introduce actually for you the terminology again in order to agree on the terminology that we will be using throughout this semester. Now, here what you see here is a fact, okay? The parent is the predicate symbol, and now I'm having actually two arguments. And it turns out that the two arguments of this fact are constant. That means Muhammad is a constant and Ali is a constant. Okay, and constants are considered to be the simplest type of terms, okay, that define structures in this case. But the structure is an easy one in this case. Okay, a constant can be considered to be a term. Now let's go down, and then you will see a rule. Okay, the rule has also predicate symbols. Father is a predicate symbol, parent is a predicate symbol, and male is a predicate symbol. Okay, now the rule consists of a head, okay, and a body. And if you take a look at the arguments that the predicate symbols are taking, you will see that actually I'm using uppercase, and in this case we are talking about variables. Thus, a variable is a term too. The question is, can I build, let's say, more complex terms in this case in order to have a better structure for my data? And the answer is yes, but we will see that actually in a few minutes. Now, look, if I want actually to check whether someone is a parent or not, then actually the idea is just actually to write parent X, and then, for example, Salah. Okay, X is a variable, Salah is a constant. Both of them are considered to be terms. Thus, actually, the result that I'm getting here is that X is equal to Nada, or X is equal to Midu. Okay, now the question is it possible to write something of the following form? Okay, male of X, and then, for example, Y. Now, look, Prolog will not complain in terms of syntax. However, you have actually to understand this one. Now, what I'm asking is the following. Do I have actually information about whether male X and Y, okay, or male of X is a parent of Y? Thus, it's clear looking in, let's say, the set of facts that I will be having, I do not have anything that matches, let's say, the parent of male of X and Y. Okay, that means if I write it here down, okay, with the matching, okay, or unification that we introduced last time, okay, if I have, let's say, parent and then Muhammad and Ali, okay, then in this case let's go actually step by step. The parent, okay, predicate symbol, okay, unifies with the parent predicate symbol to the right. Y unifies with Ali. However, male of X as a structure, okay, its value is male of X. It doesn't actually get evaluated. That means within a predicate symbol, you shouldn't actually assume that you can call another predicate symbol, because a predicate symbol returns either true and false. That means even if, let's say, a programming language would allow that, then actually this one doesn't make sense, because male of X will be either true or false, and you cannot actually ask a question, is true a parent of Y, yes or no? And that's why the unification here will give me false. Okay, thus let's go and let's take a look at how we can actually build structures and what's actually the aim of it. I will start actually small. Thus I will be having a person, and the person is having a name and a last name. Thus if I'm having someone who is called Ali, okay, and his last name is Ahmed, okay, and let's say his age is 19, okay, then this information can be built with a predicate symbol that is a ternary one, okay, having 3 arguments. And here I have actually to know exactly, me as a user, okay, whether Ali is the first name, the last name, okay, or something else, okay. The 19, okay, it has to be, let's say, known for the one who implements it, whether actually this one corresponds to the age or the weight. Now, for sure, what we can actually do is we can just build something where we define a more complex term in order to organize the data in a better way. And that's why what I will do is I will write actually something of the following form: first name Ali, okay, and then last name Ahmed, and last but not least I will be having age 19. Okay, now what I can do is I can take another person, okay, then in this case the first name will be, for example, Nadim, okay, the last name will be Mina, okay, and last but not least the age will be equal to 22. Okay, now once I will save and I will just consult. Now what I can do is I can ask about a person of X, Y, and Z. Okay, thus what you will get here is you will get actually the following. Okay, the binding is that X, which is my variable, is equal to first name of Ali, which corresponds actually to now to a term. Okay, and once you read it, you will understand here that Ali is the first name of the person, and then you get Y is equal to last name Ahmed, and Z is equal actually to age. And if you want actually to get, let's say, the second hit, then we type semicolon, and then we get actually first name Nadine, last name Mina, and age 22. Okay, as a result for person of XYZ. And again, the meaning of this one is that person of XYZ holds if either X is equal to first name of Ali, Y is equal to last name of Ahmed, and Z is equal to 19, or X is equal to first name of Nadine, Y is equal to last name of Mina, and Z is equal to age. Thus, what we could do is we can actually, let's say, do the whole thing with the following query: first name Ali, okay, and I want actually to know the age of the person. Thus I don't care about the last name of the person, and what I want to do is I want actually to get the age. Thus I will be writing age Z, and here what you will get here is it's just a unification, and I will unify person first name of Ali, okay, underscore is a wildcard, means I don't care about, let's say, the variable itself. I will not get it as a result, as a binding, and Z in this case will be bound actually to age of 19. Now what you can do is, if you want actually to get only the 19 as a result, you will actually call the query with person first name of Ali, okay, comma wildcard, comma age of Z, and the result that you will be getting here is Z is equal 19. Okay, thus just to summarize, okay, if we want actually to think about a term, okay, a term in Prolog can be either variable, let's say X, Y, Z, okay, these are variables, or I will write it in lowercase a, b, c, which corresponds to constants, or something of the form f of, let's say, t1 till tn, okay, where f is a function symbol and it will remain always uninterpreted if you will use it, and t1 and tn are terms. Okay, that's the t1 and the t1 and the t2, can be, let's say, any terms in this case, meaning I can build something which is more complex, okay, just to have a kind of nesting of terms in this case. Okay, that means what I can do is I can write something of the following form: f of g of a. This would be considered to be a term 2. If I'm using as a predicate inside, let's say, the predicate symbol, it won't actually get evaluated. And once you will go actually for the unification, you have actually to use the same structure in order that your query will unify with one of the facts or the head of one of the rules in this case. Okay, this is, let's say, roughly the main concept of structures. And now what we want actually to do is we want actually to think about a structure to define numbers. Okay, and after that we want actually to define some of the predicates dealing with numbers in this case. Okay, yes, let's go and see what we can do here in this case. Okay, we want to deal with natural numbers. Okay, and natural numbers are let's say numbers that are positive, meaning we want actually to deal with 0, 1, 2, 3, okay, till infinity. Okay, now if you want actually to deal with these numbers, you have to find a kind of finite representation of them. Okay, I know that the set is an infinite one, but the question is it possible to think about a way just to define these numbers in a finite way? Okay, and now what we can do is we can actually think about the following. Okay, if I am having a 0, then the 0 will be defined actually with, let's say, something like a constant, which we call actually 0. Okay, now anything else we will define it with a kind of a function symbol that I will be applying on terms. And that's why we will think about, let's say, a function which corresponds to adding 1 to any number. It's actually plus 1. Thus, this function will be a function that takes one predicate. And that's why if I want to represent 1, 1 will be represented as successor of 0. Keeping in mind, since actually we changed, let's say, the way how the 0 will be represented, now what we have actually to do is we have to write it actually in the following form. We will write successor of 0. Now once I take a look at this one, okay, the value of it will not be counted, but for users, once actually they agree on this representation, I know exactly that successor of 0 corresponds actually to 1 in this case. Now if I will write successor of 0, then I will know exactly in this case that this representation corresponds to 3. Why 3? Because you will take a look at the first successor, the second one, and the third one. Successor of 0, this one corresponds to 1. Okay, this corresponds to 1. And now successor of 1, in this case, once you will take it, this corresponds to 2. And the successor of 2 will correspond actually to 3 in this case. Okay, thus a number will be defined actually as follows. Either the number is 0. Okay, now I will write actually the definition of it. Okay, a number is either having the following form. It's a recursive definition, is either having a form of 0 or having the form of successor of n, where n is a number. Okay, thus if you take a look at this definition, then the definition is a recursive one. This is my base case. Either the number is having a form of 0 or having, let's say, the form of successor of n, where n itself, okay, is a number, meaning either of the form of 0 or of the form successor of x, and x is either a 0 or successor of y, and so on. And this will actually give us a kind of a finite representation of numbers that we want actually to deal with. Now, having said that, if this is the case, and again we will be having something of the following form, numbers will be written as either successor of 0 or as 0 or successor of 0 if I want to represent 1, or successor of 0 if I want to represent 2, okay, or in general I will write it successor of n, okay, where n itself is a number. Okay, these are, let's say, how numbers are represented. A number is either 0 or something of the form, okay, successor of 0. Now the question is, I want just to define a predicate that check the following: whether what I'm writing, the structure that I'm writing, is a correct, let's say, number with the structure that we agreed on. Thus, a number is either of the form 0. This is my base case. Okay, if it is not the case, then I will just have to consider, let's say, the inductive case, the recursive case. Then this one is of the form successor of n. And now, in order that successor of n will be a number, then n itself has to be a number. And this definition will be, in this case, a recursive one, where we are the ones who define the 0, we are the ones who defined actually the meaning of successor actually function, because the successor function won't be evaluated in Prolog, and it's not predefined in Prolog at all. And that's why now, once we have it, and then we go just to apply, let's say, to check actually this one, if I will write the following is 0, a number, for sure what I'm getting is I'm getting false, because the only numbers that now the is number predicate will give us as true will be the following: either my number is of the form 0, or, okay, my number is of the form successor of successor of successor of 0. Okay, 1, 2, 3. Thus, in this case, okay, successor of 0. Okay, let me start. This is my 0. This is the first one, second, third, fourth. Okay, and now you will be getting actually true in this case. Now look, if I will replace this one by 0, then the result will be actually false, because now once actually you will just try to evaluate it, and I will trace it actually with you in few minutes, you see that actually the last thing that you will be evaluating is something whether 0, okay, written as a 0 is a number or not, but according to our definition this is actually not the case. Okay, yes, I will trace in order to be able to understand it. After that I will draw the search tree. Thus I will do it with, let's say, is number of successor of 0. Okay, 1, 2, 3. Okay, and now Prolog actually will call the following: is number of successor of 0. The first one doesn't match, because 0 doesn't match with successor of 0. However, successor of n will match with successor of 0, where the n will be equal to successor of 0. And that's why my call is now whether successor of 0 is a number. Again, successor of 0 doesn't actually match, doesn't unify with 0, but it matches actually with successor of n, where the n will become actually a 0. That means the whole thing will be calling is number of 0. Is number of 0, okay, unifies with is number of 0. It returns true, and that's why I will exit from here. I will exit from the previous one, I exit from the third one, and last but not least, you will get actually here a true. And now the nice thing is, if you want actually to get all numbers, you can actually get it easily. You check whether, let's say, n is a number, where n is a variable, and then you get, I will remove the trace in order to see everything. Okay, Now I will call whether n is a number. That's what you will get here is it tells you is number of n is true if n is equal to 0, or n is equal to successor of 0, or n is equal to successor of successor of 0, or n is equal to successor of successor of successor of 0, and so on. And the question is, how do I get that? Let us trace it. Okay, now what I want actually to do is I want to, let's say, check the following query. Okay, let's have it in now. The check is number of n. Okay, now if you take a look at, let's say, how the whole thing is implemented, I will be having two different branches. Okay, the first branch is the following. Okay, it will match with the first one. Okay, where here I will be having n is equal to 0, and this one will be, let's say, done. Now the second step will be that let me go down and let's try actually to do it here. Okay, again, if I have is number of n, then I will be having two alternatives. The first alternative is that I will be unifying with the first one, then I will get n is equal to 0. And the second one actually will be that the n will be equal to successor of let's say a number x. Okay, and the check will be is number of x. Okay, now once I will go here, okay, I will go and check whether, let's say, x is a number. The first one is I get actually that x is equal to 0. And now what you have to do is you have to propagate this one actually backwards. X is a 0, meaning in this case n is equal to successor of 0, and this will be the second, let's say, thing that will be displayed. Meaning here, okay, the first thing that will be displayed here, okay, after displaying the 0 is that n is equal to successor of 0. Okay, this is, let's say, the x is equal to 0 since n is equal to successor of x. Okay, the result that I will be getting here is that n is equal successor of 0. Okay, then I will go further, and here you will have an alternative is number of x. Okay, will unify with the second rule, where x will be equal to successor of y. And now the question is y a number, yes or no? Okay, now once you will go here, you will have actually also two alternatives. The first alternative is just to go and have y is equal to 0. You propagate it actually backwards. Y is equal to 0. The x will be equal to successor of 0, and the n will be equal to successor of 0. And that's why once this one actually will be executed, I'm done with the execution of this branch, and the n will be equal to successor of 0. Okay, and this one will go actually into is number of z, and then actually this one will have actually two alternatives, where the z will be equal to successor of 0, and the n will be equal to successor of 0. And this is actually the way how we will get all results in this case. Okay, thus you will see that at the end of the day you will be getting, let's say, all results, okay, and you can actually go further, and all results will be displayed from 0 till infinity, and that's why I will not be able to collect them in the list, because the list will be an infinite one. Okay, nice. Now the question is, if I have actually the structure defined, okay, keeping in mind that the statement, okay, successor of n is something which is not predefined in Prolog. Prolog will not be able actually to understand it, meaning you can actually change it just actually to have it s of n in order actually to use, let's say, the function successor. Now once you do that, okay, I will go here, I will remove the trace, I will just display it, and if I will ask actually the following, whether the successor of 0 is now a number, okay, don't wonder that actually the result will be false. Why? Because Prolog will not be able actually to understand what the function symbol suc will mean. Okay, however, if I will take it and replace this one by s, which is actually defined in our program, okay, then in this case you will be getting true. And if you want actually to check all possible numbers, okay, then you get n is equal to 0, and then actually the rest would be s of 0, s of s of 0, s of s of s of 0, and then you get actually all let's say representations of all numbers in the form of either 0 or s of something. Okay, now let's go further, and then we want actually to define a predicate, okay, that will give us actually the value of a specific number given in a representation of 0 or s of something. Okay, that's if I have, let's say, something of the form 0, I know exactly that its value corresponds to 0. And now if I am having something of the form value of s of x, okay, then I know exactly that the value of it will be calculated as follows. If someone will give me the value of x, okay, assume it's n1, then in this case I will be able actually to build a kind of relationship between the n and the n1, okay, where n is equal to n1 plus 1, okay, because if I have the value of x, then the value of s of x is, let's say, the increment of x actually by 1. Now let's see what we get here in this case. Okay, now if I will go and call the following, okay, value of 0 and l, what I will be getting here is I will be getting l is equal to 0. And if someone actually will write the following, okay, value of l and 0, then I think it will work actually in both directions, where I will be getting l is equal to 0. Okay, that's if I am having actually a 0, then its corresponding representation will be 0 in this case. Okay, now the question is, what about the following value of s of 0, 1, 2, okay, l. And now what you will get here as a result is the following: l is equal to 0 plus 1 plus 1. Okay, we remember exactly what we did in arithmetic. Here I'm using equality. Equality means unification. It doesn't actually evaluate the right hand side expression, and that's why what I will do is I will replace the equality by s. Now what we will do is we will go and we will reload, and we call actually the value of s of 0, and what you will get here is you will get l is equal to 2. And the nice thing is the whole thing actually can work perfectly, okay, in reverse actually direction, meaning if I have s or I have, let's say, something which is x and it is having actually 4 as a value, then what I need actually to see is that the x actually consists of 4 s's, and you get it actually correctly here, okay, that the whole value is equal to s of 0 in this case. Okay, thus it works. And then I think is if you do it with x and y, you will get actually all possible alternatives. It tells you if x is equal to 0, then y is equal to 0. If x is equal to s of 0, then the y is equal to 1. If x is equal to s of 0, then the y is equal to 2. And last but not least, if x is equal to s of 0, then the y is equal to 3. And you can actually get all possible actually solutions in this case. And this is actually with one single, let's say, definition of a predicate. And you see, due to the fact that the, let's say, statement is a declarative one, okay, here it can be used in both directions. It's not only a unidirectional where I give an input and you get an output, but in this case you can give an output a value, and the input doesn't actually have a value, and the input value is the one that will be calculated in this case. This makes, let's say, the programming language more declarative than any other programming language that we saw so far, if you compare actually Prolog with Java or with Python. Okay, this is nice. Now we will go further, and we will think about the following actually problem. Okay, what I want to do is I want actually to perform the addition on structures, meaning if I have, let's say, something of the form s of 0, and I want actually to add it with s of 0, okay, this is an addition that I want actually to perform, then the result actually should be in this case s of 0. Okay, thus again I want actually to perform the addition of x plus y. That will give me actually a z. However, just actually keep in mind the x, the y, and the z will not have actually any values except actually the structure either 0 or s of something. Okay, now the question is how can I implement actually this one? Okay, first of all we need a predicate, and the predicate will be called, let's say, addition. Okay, I will call it add s, in order actually to know that the addition that I will be performing is not the addition of, let's say, values, but the addition of structures. Okay, this one takes 3 parameters, x, y, z, and this one holds if and only if, okay, the z corresponds to, let's say, the addition of x and y. Okay, now the question is how can we do it? Okay, now it's quite easy, because actually I know exactly if this one is a 0 and it will be added actually to anything, then the result will be always equal to this anything. Okay, thus the base case is an easy one. Okay, let's go and try actually to implement. I will be having, let's say, an addition. Okay, it's an addition of s. The first argument is 0, the second argument is 1, then I know exactly that the result will be always equal to 1. Okay, thus once I have it, and I will just make this one, I will load it, and then I will be having add of 0 and something of the form s of 0, okay, 1, 2, okay, and add. Then in this case there is a result s of 0, 1, 2, it's add of s, okay, add of s of 0, then actually the result will be equal to s of 0. Here I didn't actually write add of s, and that's why I got actually this error, because it called the addition that have been defined actually before, where you are actually performing an addition of x plus y, and it has to be evaluated. For sure this one actually will give me an error, and that's why here on purpose, okay, I'm using, let's say, a new predicate symbol, which is called add of 0 in this case. Okay, now just actually look at the following. If I will be having add of let's say something of the following form, s of 0 and s of 0, this one will not work because I'm not actually defining, let's say, the case yet, and it doesn't again, it has to be add of s, add s, okay, This one actually would give me false because it doesn't actually unify this fact at all. Okay, yes. Let's go and think about, let's say, the recursive call. Okay, again, it's an addition that I want actually to perform, and I'm having already actually the base case. Now the question is, what would have happened if I'm having an addition of x plus y, and the whole thing actually will give me z. However, okay, the first case was that this one is a 0, this one is a y, and that's why this one actually will be equal to y. This is actually the base case scenario. Okay, this one has been already implemented. Now the question is, what if my x is of the following form? It's successor of x plus y. Okay, now the question is the z. How will it look like? Okay, I know exactly that this one will be of the following form. It has actually to be of the form successor of something. Okay, the successor one actually will appear here. It's successor of z1, where this z1, okay, corresponds to the addition of x and y. Okay, meaning, in other terms, if I want actually to do it, let's say with numbers, okay, if I have the following, okay, successor of x will corresponds to x plus 1, okay, plus 1, okay, this one is equal to x plus y, and the whole thing plus 1. Okay, thus this one is the successor of the addition of x and y, and this one, if you read it like that, is the successor of x, okay, added to the y in this case. Okay, thus if we want actually to implement it, then we have to think about the following structure. Okay, you are having successor of x, you are having a y, and you are having a z. Okay, I know exactly that the z has to be of the form successor of z1. Now the question is, why does it have actually to have, let's say, at least one successor actually function? I will do it with the s in order actually to have a short representation of my numbers, s of x, y, and z, and the z has to be of the form s of z1. The question is, why does it have actually to have an s of something? Okay, because if you add x plus 1 plus y, okay, it's for sure, okay, you will be getting, let's say, as a result, at least one s. Now the only question is, what will be my z1? Okay, z1 corresponds to the addition of x and y, and this one you will get it actually as z1. Okay, now if I will compile, and I will go and make actually this one, and then I will call the following add of s of 0, okay, and then s of 0. What I should expect here is a result where L is equal to s of 0, and this one actually will work perfectly. And now if you have something like s of 0 and s of 0, then in this case you will be getting 3 s's actually as a result. And if you will take this one and you will do it with s of 0, then you will be having 3 plus 1. 3 plus 1 should give you 4, meaning the result will be represented as s of 0. And now you can actually combine to make sure that actually everything is correct. You will take it, you will have actually the value of L, and last but not least, okay, the value of L will be actually, let's say, converted into a number, and which is n. That means in this case you get actually that the n is equal to 4. Okay, the value has been already implemented before. Addition actually will perform the task in this case. Okay, I hope actually this one is clear. If not, then I would love actually to trace it with you. Okay, I will just erase, let's say, this part, and try to trace, let's say, a simple query, okay, that consists of the following. Let me wait. Okay, let's go and trace the following. I will have an addition to be performed actually with two numbers. Okay, that's the first one will be a kind of an addition of s of 0. Okay, then I will be having s of 0 and then actually a result z. Okay, the only rule actually that will unify, if I will go and show you this one, is the second rule. The head of the second rule will unify actually this one. Okay, then I will be getting actually the following. Okay, I will be getting that. Okay, I will do the unification itself. Okay, s of x, and here I will be having, okay, s of 0. Okay, thus in this case s of 0 will be actually unified with s of x1. I will rename actually the variables. Okay, and then my y will unify s of 0. Okay, thus this is my y1, and last but not least the result is, let's say, z1, which is equal in this case to my z. Now the call will be, let me add, okay, s of 0. Okay, and then I will be having s of 0 that will not change, and last but not least a new variable which is actually z2. Okay, keeping in mind that before actually doing that, okay, the whole thing actually will be done that my z here should be equal to s of z1. Okay, and that's why I will write here a statement, okay, that here my z, okay, will be equal to s of z1 in this case. Just actually keep that in mind. My z, which is the value of the z, is equal to s of z1, and the z1 is, in this case, since I renamed, is actually z2. Now, the only one that I will actually be able to evaluate in this case is the following. Add of s of 0, okay, will be add of s of 0. This one will not change, is z of 0, and last but not least z of 3, where z2, okay, is equal to s of z3. Okay, now having said that, if I will go up, okay, with this one, then the whole thing will have actually the following form. Add s of 0, and z of 3. The only head of the rule that will unify is the first one. That means in this case I know exactly that z3 will be equal to s of 0. If z3 is equal to z of 3, you will just actually propagate it back. Then the z2 will be equal to s of 0. I'm replacing the z3 by s of 0. Now this one will be propagated actually back, okay, where the z will be equal to s of z2. Thus here I will be having as a value z is equal to s of 0. And this one, if you take a look at it, it should correspond actually to the result, where the addition of 2 plus 1 will be equal to 3, and the 3 will be represented as s of 0 in this case. Okay, now the question is, if I want to define subtraction, how will I do it? Okay, now before actually doing that, let's take a look at the power of this one. Okay, and here it will answer actually the question how subtraction will be solved. If I want actually to perform the following addition, okay, s of s of 0, okay, with something that I really don't know, and the result actually should be something of the form s of s of s of 0. 1, 2, 3, 4, 5. Hope this one is correct. Okay, and what you will get here is you will be getting actually a nice result that the L has to be equal to s of s of 0. Now if you will go, okay, and you define, let's say, this one with another s of 0, now you will see exactly what will happen. Okay, the L has to be equal to 3, and you will get as a result L is equal to s of s of 0. Okay, now if you will do that and you do not know actually the first operand, I would call it a L, and s of s of s of s of 0, now you are having actually different ways how this can be done. Either my a is equal to 0 and L is equal to 4. Okay, this is actually one alternative. Or my a is equal to 1, which is of the form s of 0, and my L is equal to this is 5. 1, 2, 3, 4, 5, yes, and my L will be equal to 4. Okay, that's this one actually will give me 5. Either my a is equal to 2 of the form s of s of 0 and L is equal to 3. Okay, or let's say my a is equal to 5 and the second operand will be equal to 0 in this case. Okay, without actually doing anything, everything actually will be calculated for me. And last but not least, if I will take it here with a, L, and z, you will be getting actually all possible, let's say, alternatives and all possible results. It tells you if a is equal to s of 0 and z is of the form s of and L is equal to z, that means I don't know actually its value, then z has to be actually for sure of the form s of L. Thus it gives you actually all possible let's say combinations depending on the implementation that we will be having. Okay, now having said that, I want actually to subtract without actually subtracting. I want actually to use the addition actually to subtract. Now the question is, how can you do it? How can you subtract x plus minus y? Okay, it's quite easy. Okay, in math, what you can do is you can actually think about the following. Okay, if I want to subtract, what I will do is the following operation. Okay, let me go here. I will remove actually this one. Okay, and now the whole thing is it's actually performing x plus y is equal to z. Okay, now the question is, if I want actually this one actually performs the addition of add x, y, and z. The question is, what if I want actually to perform the subtraction of x, y, and z? How can I do it? Okay, this one actually holds. Okay, x, if you write it in math, you have x minus y is equal to z, meaning the x has to be equal to y plus z. Okay, and that's why this one actually corresponds to an addition of y and z that will give me x in this case. Okay, again, x minus y equal to z corresponds to subtracting from xy, and the result will be equal to z. I will take actually the y to the right hand side, that means x is equal to y plus z, and I have already actually something that performs the addition of let's say x and x, y, and z, and this is, let's say, something that we have already defined actually before, where addition y, z, x will be actually performed in this case. Okay, let me go, and then what we will do is we will write actually the subtraction of x, y, z corresponds actually to the addition of, let's say, y, z actually to get me an x in this case. You compile, okay, you run, and then you want actually to do a kind of a make. You subtract from s of 0, okay, s of 0, and the result actually should be in this case s of 0, and you get actually s of 0. That means if I get let's say s of 0, and I subtract from it s of 0, then actually what I'm expecting is a 0, and you get as a result as a 0. If you take actually this one and you have s of 0, then in this case I have to add 2 brackets, then actually the result will be s of 0. Okay, since you are subtracting 2 from 4, and the result actually will be correct, as you can actually perform the addition through, let's say, performing the subtraction in this case. And the nice thing is, as I said actually before, if you have actually this one, okay, and this one is my L, okay, and the result is s of 0, okay, the whole thing actually can work properly, and you get actually the correct result too, where the L will be equal to s of 0, which is actually the second operand, meaning if I subtract from 4 2, then the result will be 2 in this case. Okay, nice. Let's go to let's say the data structure, which is already predefined in Prolog. However, what we want actually to do is we want actually to define one user defined predicate, and we want actually to implement some of the predicates, okay, that deal with this data structure, which is actually about lists. I will go, and what we will do is we will erase شوية, okay, and then the question is, if I'm having a list, okay, the list corresponds actually to a collection of data. I can have duplicates in it, and what I want actually to do is I want actually to find a way to represent, let's say, something of the following form: a collection of data, okay, having 1, 2, and 3 in this case. This is actually my list. Now, first of all, we have to define actually how a list is defined recursively. A list, okay, can either be empty, okay, or something that has a head, which is an element, and a tail, okay. This one is an element, and the tail will be a list. Okay, now if you take a look at actually this definition, then this definition is a recursive one, meaning in English we will say a list is either an empty one or something that consists of a head, where the head is an element, and a tail, and the tail is a list. Meaning 1, 2, 3 is a list because it has a head which is 1, and a rest list which is equal to 2 and 3. And now what we want actually to do is we want to think about a structure actually to define it. Okay, now it's easy, it's simple. Okay, for empty we will just actually give it a name. We will call it nil. It is, let's say, motivated by the functional actually programming language, where an empty list will have actually a specific name. It's called nil. You can call it whatever you want. You can call it empty. You can call it whatever you want. And now the other one will be actually something of the following form. If I want to represent 1, then 1 will be represented as a list that consists of 1, and then a tail, and the tail actually will be nil. If I have a list that consists of 1, 2, 3, then I will be having something of the following form. The list is having a head, and the head is 1. Thus I will be having list of 1, and it has actually a tail here, and the tail actually should correspond to the list 2, 3. How will I define it? I will define it recursively, where the list is having, let's say, 2 as a head, and a rest list, which is actually in this case the 3. Now how will actually the 3 will be defined is as list 3, and last but not least nil, in this case 1, 2, 3, and this is actually the representation of a list that consists of 1, 2, 3 in this case. Okay, 1, 2, 3. Okay, 1 is the head, and this is the rest list, which is 2, 3. Now 2, 3 is a list of 2 and list of 3, and nil in this case. Okay, now this is a structure that we want actually to define, and we want to use just actually to implement actually something of the following form. I want actually to define, let's say, a predicate called length. Okay, I will call it length 2, okay, of a list. If it is nil, then actually the length of the list will be equal to 0. If it is not nil, then it's of the form, in this case, list of something. Okay, now this one okay, will be having actually the following format. First of all, if it is of the form list of something, then in this case it consists of, let's say, an element which is X and a tail list. I will call it head, okay, and tail. Head is the head of the list. That's what I will do is I will compute the length of the tail. This is N1. And last but not least, we have actually to find a connection between N1 and N. Now, I know exactly that N1 is equal to N plus 1. Okay, now, once we do it, and then once we compile, everything will work except that I will be getting a warning. Why am I getting a warning? Because actually the head is defined in the head of the rule, but it's not used in the body of the rule. Prolog actually will warn you, will tell you, you could have a problem. It could be that you forgot it. Now you will say, no, if I want actually to check the length of a list, I don't need actually to know the value of the elements themselves, but I need actually to know that they are, let's say, that they do exist in my structure, and that's why I will be using an acronym in this case, which will be written as a wildcard. Now, once I would make, okay, this warning actually will disappear. Keeping in mind that the warning is a warning, it's not an error, meaning everything will work properly, even actually with this warning. Okay, now, length 2, and now if I would be having nil, okay, and the list L, what I will be getting here is I will be getting L is equal to 0. If I will go and let's say have something of the following form, it's a list that consists of 1, a list that consists of another 2, and then a nil, 1, 2, and then a list L. Then in this case I should expect as a result actually something of the following form. One moment. N1, it's not N1, this is actually my mistake, it's N is equal to N1 plus 1. I get actually the length of the tail, and I will add 1 to it to get actually the length of the bigger actually list. Sure, this is my bad. Now I will be having it actually with me, this one, okay, I didn't save it, okay, now you will make it, okay, you will call it, and then you get actually as a result L is equal to 2. Okay, thus this is exactly how you will be able actually to get actually the length of the list, and you can actually have a list which is a little bit larger. Okay, thus I would be having list of 3 and then nil, and the total number of elements will be equal to 3. And last but not least, what I can do is I can have a length of a list L which is not defined, and I know exactly that the total number of elements will be equal to 5. And the right thing is, what you will get here is you will get actually a nice result that the list has to be of the form list of, list of, list of, list of, list of, okay, 5 times, okay, in order actually to state that actually the list will have actually, let's say, 5 elements. If I am having actually 2 elements in the list, then the list has actually to be of the form a list of something, comma, list of something, comma, nil. Okay, now you can actually take actually this predicate easily, and what you can do is you can change it, let's say, by something that will give you the summation of the values of a list. If the list is empty, then in this case the summation of all the elements of the list will be empty. However, if I will be having a head and a tail, then I will be expecting first to get this summation of the list. This is, let's say, the sum of the list of h and tail. Then in this case the n will be equal to n1, meaning in this case h plus the n1 in this case. Okay, thus once we go and we compile, we first of all load this one, and then you call the summation of a list that has as an element 10 and a list that has as an element -3 and nil. And what I want to do is I want actually to check, let's say, the summation of all values. 10 plus -3 will give me 7 in this case. Thus the, let's say, way how you are implementing is almost actually the same as the length, with one difference. okay, I will be getting the value of the head. I will sum it up actually to the summation of the elements of a tail list, which will be stored into a variable called n1, and that's why the n will be equal in this case to n1 plus h in this case. I hope, let's say, this presentation is clear. Once we go to the tutorials, you will take a look at, let's say, different other data structures like trees, okay, where a tree in a nutshell is defined similar actually to a list, okay. If you want me actually to introduce it slightly, this can be done actually easily, okay. A tree has actually either the form of being empty, that means it's an empty tree, okay, or actually is something that is having a kind of a root, okay, and a left subtree and a right subtree. And that's why if I have a tree of the following form, 5, 6, and 7, and you want me actually to represent it as a structure, you can define it as the following. It's a B tree. The B tree will be having 5 as a root. And now I will go and represent actually the part where it corresponds to the left subtree. The left subtree is having BT, okay, and then 6. And the left subtree of 6 is nil, and the right subtree of 6 is nil. Last but not least, if I want actually to represent the right subtree, this one is also a binary tree that is having as a head BT, okay, and this one is nil, and this one is nil. This is actually how the representation of a binary tree would be done. Thus, the function symbol would be the BT, okay. This is my function symbol, and it's a recursive actually definition, because we know exactly that a binary tree is either an empty one, which would actually denote by nil, or something that has a root, okay, this is actually the value, and a left subtree and a right subtree. That means it has always actually to have the following form. And what you can do is, once you agree on this structure, you can define any predicates just actually to perform the operation that we did in CSEN403 in the data structures and algorithms to traverse actually the binary tree, just actually to count the total number of nodes. And this is actually something that we will be doing in the tutorials and the labs, and you will be able actually to practice that with more complex trees in this case. Okay, thank you very much. Have a nice evening, and see you soon.